Well, good morning, everyone. I'm Dan Reed, moderator of this session on reproducibility in HPC, a passing fed, a work in progress, and in my traditional role of moderating the final panel of SC. It seems to be what I do almost every year. So we've got a great lineup. I wanted to try to set the stage a little bit and then introduce the panelists and the order in which they'll speak. I started the conference Monday evening chairing a plenary panel about ethics and HPC. Today we're going to talk more about the technical aspects of ethics, in particular around reproducibility. And I want to show a little bit of data from a science paper from 2016. And it's obviously a bit skewed toward the biological and physical sciences, but it asks some basic questions. Is there a reproducibility crisis? In other words, can research results that are published be replicated by other people? And as you can see on the left, the majority of people say there's a significant crisis, and others say there is at least a slight crisis. Other questions asked in the paper were what factors contribute to irreproducible results? And their variety, as you can see, there are everything from pressure to publish to methods and code unavailable, something that's relevant to us, to raw data not available, to bad luck down at the bottom, and also just plain fraud. There are an increasing number of papers being retracted because the data has been fabricated in many cases across science. So that contributes to the level of trust that our colleagues, not only in science, but outside science and the lay public have in whether science is in fact a rigorous process. The other part of the survey asked questions about what factors support reproducibility, and not too surprisingly, in a lot of science, better understanding of statistics is at the top of the list. There's an old joke in astronomy back when data was rare and hard to acquire that I found 3 instances of a thing and now I can do statistics on them. And so there's a reason why in high-energy physics 5 nines is the standard of excellence, because extraordinary claims do in fact require extraordinary proof. And we've seen lots of cases where p-tests with very weak statistical validity have led to claims that later had to be retracted. We obviously have some different aspects in high-performance computing about how we think about reproducibility. In some cases, access to unique infrastructure, but code and other issues. It's been why there's been so much focus on packaging technology of various kinds to allow consistent replication of the underlying software base. So if you think about all those issues, in particular around HPC and how it relates to reproducibility, as I said, there's sometimes some issues around very access to the infrastructure, the code, the data. There can be confirmation bias in the way that we interpret data. There can be, in some cases, one hopes rare, but nevertheless not zero, cases of misconduct. We tend to think of the execution environments in which we run code as benign, but attacks, cyber attacks on research infrastructure, particularly in higher education, are rising rapidly. So there are issues around malware and what's actually running on your system. They're just plain old errors. We know that computational models by definition are approximations, and so many of the questions about domain of applicability of the models, particularly as we couple multiple models and we build AI trained based inner loops for some aspects. Are we stretching the models out beyond the domain where they have been validated and can be trusted? Obviously, the other aspect of errors is just plain old correctness. Have there been algorithmic errors introduced into the code? Clearly unique scale at the high end. There are a limited number of such instruments, and so reproducing in other environments may be challenging. So all of those things and a host of others, including publication culture, are a piece of how we think about this intersection of ethics, HPC, and reproducibility. And so our panel today will talk about a whole range of these issues, and we will not necessarily follow this order. We're going to start with Lorena, and then we will move to the others. And I think Beth and Tom may well bring up the end just for simplicity with our virtual as well as in-person panelists. So with that, I'm going to hand the floor over to Lorena. Remember, we'll be moderating Hub for questions, so please don't hesitate to inject questions there. And so, Lorena, I'm going to stop sharing my screen and turn the floor over to you.
Thank you ever so much. And I am not going to use any slides, so just the camera feed will be fine. If you can pin that video for the display, that will do. Thank you ever so much for inviting me to this session. The convocation for which, of course, challenged us quite a bit with the idea of whether, the question of whether reproducibility is a passing fad. And for sure, the interest in reproducibility has really increased in the last decade or so. And you see conferences now with reproducibility challenges and journals that request code and data statements, funding agencies that issue dear colleague letters and new data sharing policies. And of course, SC with the Reproducibility Initiative now over 5 years old. And I myself served as reproducibility chair in 2019, the year that saw the initiative moving under the technical program, artifact description appendices becoming mandatory, and 3 new tracks added to organize our efforts in this topic. So why are we doing all of this? Especially in the context of high-performance computing, when we know that we hardly ever will actually reproduce the costly, formidably long, and specialized computations. Access to supercomputers is limited, computing allocations are finite and competitive, machines are upgraded or decommissioned after a few years. So what is the meaning of reproducibility in this setting? I want to propose that the goal is to, over time, implement and recognize trustworthy computational evidence, not by actually exercising the open research of objects or artifacts shared by the authors, that is the data and code, but by a research process that ensures unimpeachable provenance. The definitive policy-informing report of the National Academies sharply focused the definition of reproducibility, obtaining consistent computational results using the same input data, computational steps, methods and code, and conditions of analysis. This definition indelibly links reproducibility with transparency, via the requirement that data and code associated with the research study be made available to other researchers. It doesn't say how we can achieve it, nor how we might corroborate or confirm that it is achieved. So what makes a computational study trustworthy? As a case in point, I want to discuss the role of open source software in reproducible research. The definition of reproducibility only says that the research software should be available. It doesn't suggest that it needs to be open source. Now, some pioneers of reproducible research did argue that the software should be made available under a license that grants the freedoms to reuse, modify, and redistribute the code. But some, like myself, want to go further. We want research teams to go all in and adopt the open development model. Why? From a legal perspective, open source is a licensing model. When applied to research software, of course, it contributes to transparency of the computational workflow and availability for others to use, modify, and redistribute the software. That's a requisite for reproducibility. Transparency is necessary, but not a sufficient condition, however. We all know reproducible research implies the ability of another researcher or team to reuse the data, code, and conditions of analysis of a published study. The key operating word here is reuse, which, as any researcher who has tried to exercise the digital artifacts of another will attest to, can be laborious and sometimes impossible. An open source license does not by itself support reuse. Good quality software design and documentation are needed in at least some measure. And so in support of software quality, the open source development model takes center stage. Some guiding principles of the open development model are the mantra, release early, release often, the idea of cultivating users as co-developers and making full use of the internet for distributed collaboration. Developing in the open is conducive to improved quality because users can make source-aware bug reports and cooperate with developers to usefully identify issues and devise solutions. And also, when open source software projects nurture a community of users and contributors, problems are identified more quickly, software design and quality improves over time, user documentation can be made more friendly and complete, and all of this helps the software to be more reusable. And on top of that, the communities of open source software have evolved some coordinations, roles, and tooling that expressly mediate distributed teams and contributors. Users outside of the original team who are interested in the software make their own copy of the source code. They can make changes in their copy. And if they would like these changes to be adopted by the original team, they can make a move called the pull request, where they present their software to be peer-reviewed and considered for merging into the original code base. If the original team has decided that they will consider such pull requests, depending on their staffing, members taking a specific role called the maintainers will review the proposed changes and engage in a conversation with the user contributor to understand it, test it, request adjustments, eventually approve or reject it. And to facilitate this, developer communities have instigated formal processes and created technologies that enable it. The teams adopt increasingly software testing methodologies, automate the process of building from source and running the test through continuous integration, appoint leaders to conduct decision-making or governance. And these practices further contribute to maintaining and improving code quality and facilitating reuse. And so I looked for some explanations of the success of open source development using two perspectives that I want to tell you about. One is somewhat recent, and the other one is 35 years old. The first is a framework that comes from learning researchers, human learning, that is. It's a framework called connectivism, also characterized as a learning theory for the digital age. And the second is the language action perspective of Terry Winograd and Fernando Flores from their book, Understanding Computers and Cognition. The connectivist theory of learning sees knowledge as distributed across a network of connections, created and shared by an interacting community of individuals. And now, under this lens, science is the formation of connections between concepts, artifacts, people, theories, all of that. The role of the scientist is to be literate in this form of conversation, being able to traverse fluidly the network of connections and build it further. Openness in this setting is a property of the network that makes it more successful for learning, that is, to develop shared knowledge. Other properties like connectivity, diversity, and autonomy also make it successful. So open sharing has a pedagogical purpose in this framework. Openness increases our capacity to create knowledge together. And quoting co-founder of Connectivism, Stephen Downes, when he talks about open education, he says, openness is about the possibilities of communicating with other people. It's not about stuff, what we do with stuff. It's about what we do with each other. So because openness promotes rich networks, lively communities, and fertile connection, it is good for science. And open source software projects, their culture of creating communities, therefore, have more to offer than just a scheme for securing freedom from copyright restrictions on the code. Open source communities have developed templates for coordinating the actions of diverse groups of people aimed at improving communication and working more effectively together. The ethos of open source culture favors open development, network collaboration, community around open source projects, and a value-based framework. And so is that open source projects build organizations with really strong commitments to freedom of access and transparency and joint governance and decision making. And so we have some technologies that have come into play in this, like GitHub, that creates structured conversations with teams adopting rituals of collaboration, really, and associated terminology to enable them to create value together. Now, if we go back 35 years, so the 1980s, Terry Winograd and Fernando Flores were at the time concerned with designing computer systems, maybe GitHub, as an example, that can support humans to be more effective together. And they made a key observation that people coordinate their actions in the context of conversations. So language is not simply a way to transmit information about the world, but it is the way in which we change the world. It has dimensions of acts. We invent the future together via what they call conversations for actions. So from this perspective, we can explain the success of open source collaboration. Take the pull request, for example. It's a basic coordination in the open development model. One person makes some change to a code, another person reviews it, requests changes, it is merged or not. It is all a conversation. And all these moves are standard in the open source communities. Everyone knows how to act depending on their role. Subject to time and effort constraints of those involved, the software team evolves, project grows, and builds quality. GitHub as a tool just structured these conversations. And that's how it became a tool of the trade and in the open source world supporting the workflow. So a similar example is the issue tracker. A project's contribution policy may ask to log an issue for any question. And implied in this policy is a commitment to coordinate actions for addressing the issue. In fact, a public version control repository is a signal that the project is open to users participating in the development process. And it is common to view a public issue tracker as a strong indicator of the project's commitment to openness. So how is all of this conducive to reproducibility, in my view? Well, reproducibility is about trust. And it is often in the instances where trust breakdowns occur that we start paying attention more sharply to trust-building activities. And as the rapid transition to computation and data becoming central to the scientific enterprise created this credibility crisis a lot of people want to talk about, in this setting, like, inaction would amount to blind trust or denial, which is a form of self-deception and corrosive to integrity. So we, in the computational science community, have been debating what changes we need to make to our practice to increase trustworthiness. We focused on the traits of studies that can be called reproducible. They are published transparency, they share the data and the code, they adopt good practices of data management and record keeping. Next, we find ourselves debating what to do with the shared artifacts. Should they be peer-reviewed alongside the research manuscripts? Should journals exercise the computational workflow and confirm that the results can be reproduced? Then soon we're facing monumental hurdles associated with the effort and the cost of such implementation of reproducible research, especially, of course, in the context of HPC. But trustworthiness is not the same as trust. In a nice little book also with Flores, Fernando Flores, they explain that trustworthiness is a trait that we can demonstrate. It is established by reason and evidence, but trust, the act of trusting, hangs on the experience and the frame of mind of the person who trusts, the other party in the equation. This is a dynamic and social process, and it is cultivated through commitment and action and through conversations. And so for this reason, I don't believe that it's possible to develop IT products that will fully automate reproducibility and offer this one-click solution people are looking for, because we cannot solve the reproducibility problem with any approach that takes away the responsibility of the human participants. Reproducibility is essentially about trust, and one that makes possible a more effective interdependency of research results and the associated artifacts. Adopting open source software in science gives rise to a form of social contract and a way of working that builds trust. So research has impact when the network of results and how they are shared have meaningful role in society or in the continuing accumulation of knowledge. So when computational science is part of this activity, how does open source software affect any of that? Well, by itself, it may affect very much at all, but if it is the model for how we do things, how we work in collaborations, large and small, then it can have a meaningful role, looking at it from this connectivist lens. The model for how we work with research software becomes, when we are writing and running code, we feel a responsibility. We are committed to ensuring this knowledge is injected into the network to be interacted with. In this model, we see software and data as the artifacts we create to learn with and to learn with others. And the effect on the researchers who are writing code and running it to produce results is a growing sense of value in the science enterprise. This reflects the change in culture that we need. for valuing software and data and producing reproducible research. Thank you, and I yield the floor.
Thanks. Tana, would you like to go next?
I would, and I was guessing that I had a recorded video that that would be played. I can play it on my end. I don't know what's.
Well, the video I think is really for backup if we were having network connections, so probably best to just go ahead live if you don't mind.
I see. Okay.
So I do believe we're set up to play the video.
Okay, you want to do that?
I think he has it. Yeah, no, do you have the video for Tanu? I have it downloaded on the desktop. Could you start it?
Good morning. I'm Tanu Malik, an associate professor in the School of Computing at DePaul University. My research interests are in the area of data provenance and big data systems. And I've been developing SciUnit, a system for conducting computational reproducibility. I'm also the co-chair of SC21 Artifact Description and Artifact Evaluation Committee, which I co-chaired with Anjo Wadiak Oberwagner. First of all, thank you for inviting me. In these introductory remarks, I will focus on reproducibility in HPC as the practice of conducting artifact description and artifact evaluation. ADAE, as many of the authors know, is a process that continues along with paper submission, where computational artifacts are evaluated, described, and badged. Responding to the question of whether this is a fad or a work in progress, I would say that if this is a fad, then we are late to adopting this fad. Artifact evaluation, which is full-scale reproducibility, is common at other systems conferences since 2019. For 3 years in a row, that number has been steadily going up. So if you look at OSDI, SOSP, middleware, Sigmod, ASPLOS, NeuroIPS, all of them are doing full-scale artifact evaluation. Now, some of you may say that fads are short-lived. I would say, on the contrary, we have just started. Looking at the history of artifact description and artifact evaluation at SC, till 2018, even artifact description was just optional. It became mandatory in 2019, and only in this year did we explore the full scale of artifact description and artifact evaluation, where all the artifacts were evaluated, publisher-provided badges, and these artifacts were made available through the SC website and ACM proceedings. How was the enthusiasm for this fad? Well, more than 90% of the papers engaged in artifact description. And if you look at artifact evaluation, that percentage just doubled over 1 year. How many actually did receive these badges? Well, in 2020, 38% had received the badges. And in 2021, 66 out of the 99 accepted papers went for badging. 100% got the artifact available. That means you can go to Zenodo and look at their artifact. 91% could actually be billed. that is artifact functional. And for 76%, we could reproduce the results. That means we could actually reproduce the figures in the paper. Now, you may just say that, well, this is enthusiasm. Fads have little intrinsic quality. But the fact that these artifacts are available on the SC website via the ACM digital proceedings, the experiments are described in detail through an appendix at the end of the paper, and available via SIS artifact. That means if you go and look at a paper like this, you can click at the DOI link and go to the artifact over there, look at the artifact, look at all the code and the data that is provided along with the badges. Now, who doesn't find that information useful? Some may still be skeptical. Well, I have more thoughts to convey on this. When 200 authors in the SC community were surveyed by the organizers of SC20 Reproducibility Initiative, many of them responded that, well, there is a reproducibility crisis. That is 90% of them said that there is a reproducibility crisis, and 85% that this crisis is not exaggerated. When asked whether it is sufficient to simply put code in a repository, 79% said no, that is not true. You need some other form, such as containers. 35% said that they did find the appendix information that is available from other SC papers. And this process, ADAE, helps them in their work or in others' work. I have shown you quite a few survey results. And when numbers are shown, everyone has opinions. And I think the truth lies somewhere in between, passing fad for some, work in progress for many. And to sort of validate this, we looked at specific areas in which authors voluntarily went for badging. So this figure over here is for SC21 badging. At the bottom are the specific areas that SC promotes, and the numbers indicate the number of papers submitted to these specific areas. The green line shows the number of papers, accepted papers, that voluntarily went for badging. And the purple line shows the number of papers that did not voluntarily go for badging. If we look at the characteristics of the areas, things like data analytics, algorithms, system software, programming systems, they all voluntarily went for badging in high numbers. Areas such as state of the practice, performance measurement and modeling, which are notoriously hard to reproduce, half of them did not go voluntarily for badging. And areas like machine learning, clouds and distributed computing, it was a 60-30 percentage. But if we look across, there was no single area which did not go for badging. So I would say that it is a work in progress for many, and not a passing fad for any. With this, I would leave you with a thought by William Jordan, who was a famous essayist, who mentioned that a fad lives its life in a few weeks. A philosophy lives through generations and centuries, and a principle forever. As scientists, we all know that reproducibility is the principle of conducting scientific research. I would say artifact description and artifact evaluation is a philosophy that can accompany this practice of publishing papers that we have been carrying through generations and centuries. Thank you.
Thanks. Fernando, would you like to go next?
Sure. Thank you. Thank you, Dan and Beth, for the invitation and the coordination, and to the other speakers, because I will have a chance to pick up a little bit, I think, on these themes. I am very much aligned, I think, with the perspectives that Lorena articulated, so I won't belabor her points, which I deeply agree with. And I also will not be touching upon issues that I think are very relevant to this community, which are about the specific technical challenges of reproducibility in the context of supercomputing systems and large simulations, expensive simulations. I think those are all very valid points, but we can cover them as a group, and others have spent more time on them. What I wanted to think about was a little bit, as I said, reflecting on what Lorena said, this question of fad and trust, right? Why could we potentially think that something is a fad? And as Tanu was talking about, if it's ephemeral, and it's ephemeral because it's fundamentally insubstantial. And I think I would like to contend that the question of reproducibility does go to the heart of science in ways that both Tanu and Lorena already opened up on, which is this notion of fundamentally of trust. There's an interesting question in the Slido chat that we can perhaps revisit. From my perspective, the idea of reproducibility is not to be an end in and of itself, which would in a sense make a little bit of a cargo cult fad, but instead it is a means to enable what I believe are two fundamental features of the scientific process. One is the trust that we have in the validity, the robustness, the solidity of the results that we uncover. And second, the social dynamics of the scientific process, which is a dynamic process of human collaboration, right? This old sentence, this old maxim of "we stand on the shoulders of giants," right, is all about saying that we get to see a little bit higher than those who came before us because we can build upon their ideas, upon their work. And I think reproducibility goes to both of those points. Science, I think, as an endeavor, is an endeavor that has, in my mind, sort of two complementary missions. One is sort of an intrinsic value mission that is intellectual. It is the pursuit of knowledge. It has beauty and value in and of itself in our search to understand the world, the universe around us. But it also has an extrinsic mission connected to society. Science is also meant and is valued by many because of its ability to give us tools and resources and ideas to make a better world, to cure disease, to communicate, et cetera, right? Those are equally legitimate reasons to do science. And in both of these dimensions, this intrinsic and extrinsic dimension, I think reproducibility has a role to play. The idea of trust, right, intrinsically is asking, can we trust those results? Can I believe those results? Are they solid? And how can I validate that they are solid? And I do think that the question that was asked about the notion that reproducibility obviates the need for trust, I would perhaps look at it differently. I would say that trust is something that is fundamentally a human feature of systems. If in our activities as humans we trust each other, we can work better, we will function better, and reproducibility helps us build that trust and validate that trust. And second, on the extrinsic side, on the social side of scientific activity, well, does society trust us? Do those who are not practitioners trust us? And how do we convey to them that we are trustworthy? How can they see things that they recognize as perhaps more easily trustworthy? And I think, if anything, the last few years have given us an increased appreciation for the difficulty of establishing trust around scientific ideas with the broader society, right? Whether it's climate change or the science of viruses and vaccines, right? These are probably things that are high in the mind of many in this audience. And then the second aspect of science, that of it being a collaborative practice, a collaborative social dynamic, is something that Lorena, I think, expanded very cogently on, also has these dual notions of an intrinsic and an extrinsic side. The internal one is this idea that the practices of reproducibility make it easier to collaborate, right? If I can clone your GitHub repository and it has well-defined dependencies, and even before I go installing anything, I can simply click on a binder link that opens up an executable version of that in my web browser in 30 seconds, right, without having to go through whatever weird hoops you had to go through to make it compile, and I can actually run it and validate it and maybe change a few parameters. That already opens up a level of collaboration and participation that changes my dynamic with your work, right? And so there is an element of that building process that is enabled and supported by the techniques of reproducibility. And similarly, if we can show that to others, then we can find better ways to engage with society. If we can wrap that binder in a nice little dashboard that presents those results in a way that is maybe educational, or that is meaningful to a policymaker, or that is meaningful to a scientific communicator, right? Those are ways in which our highly specialized work can connect with society. So again, in both of these dimensions of trust and collaboration, the reproducibility has, I think, a role to play. And so when I think about this with wearing a little bit of my dual Berkeley educator and Project Jupyter sort of co-lead, co-founder, I think of building tools that facilitate this and putting them in the hands of the next generation in ways that make these practices routine, right? Because what I do think is important is that this becomes the fabric of how we behave. It's precisely that it isn't a fad, right? It isn't something that we did once because somebody said it was important, but rather that we adopt. And with my students, I use a simple metaphor, which is that it's a lot better to brush your teeth and floss every day than to get a root canal. And reproducibility at the time of publication, reproducibility because your funding agency is harping on you, reproducibility because the conference won't accept your paper unless you clean it up to make it reproducible. That's sort of the root canal version of reproducibility, right? Well, now that I'm going to cross the line of publication or getting funded, et cetera, gosh, I have to do all this. This is awful. Whereas if it is a practice that we build into everyday activities, if it becomes the routine mode of operation and collaborating with ourselves, remember, you often have to collaborate with yourself when a reviewer asks for you to check something, or you discover an issue in your code and you need to update your own figures, right, from 6 months ago. If we make that routine, then the dynamics changes entirely, and we have built. There's a lot to do, and in this panel, I'm sure we'll bring up interesting ideas on where to go next. But we have built both technical ideas and practices that can be taught. I teach a course called Collaborative and Reproducible Data Science at Berkeley, which I'll be teaching a new edition on this coming spring, where we take students through the process of starting with Git, starting with GitHub, working as a team, doing pull requests with one another, doing opening issues on their research projects, and building up to the point where they present scientific narratives that they can validate from beginning to end with each other. They don't have all of the complexities of a supercomputing class, large-scale research project, but at least they become woven into how they operate as a team. And they do that not only in practice among themselves, but they also do it within the practice with the open community. They go and find papers, they go and find open data sets that are part of the literature with which they conduct these kinds of works. They follow this kind of workflow. So they find a way to engage in that social process themselves. And I think this is possible, and I think it does weave this notion of trust into the practices of science in a way that makes it something that is certainly a work in progress. It's certainly not something where every challenge has been met, but in my opinion, is not just a passing fad. Thank you.
Assuming everything behaves. Uh-oh. Well, while he's... Sorry, folks. It's going to take me just a second here to... Oh, it actually popped over, so we should be okay. Let me just get this shared. Actually, let's start that first. Then hopefully this will pop up. So we've heard some very good things about doing reproducibility, actually storing artifacts that are useful for being able to reproduce research, and that's fantastic. And you know, is it a fad? Is it not? We'll talk about that in a minute, but there are some areas that I work in pretty regularly where I'd first ask, what reproducibility are we talking about? What are we trying to reproduce, or how are we going to do it, right? What is this? And I think we have a pretty good idea when it comes to talking about reproducing experiments, reproducing running software, right? It's somebody being able to actually go take the inputs that somebody hopefully has provided, hopefully get what's in the middle, be able to rerun the software, recreate the method, what have you, and actually recreate their outputs. That makes a lot of sense. It's extremely useful. But when we start talking about energy and power measurement, things that I've run into a lot of kind of interesting issues with the Green 500, for example, or we talk about building software or actually running old software to recreate these results. What are we actually talking about? What are we doing here, and how does it actually work for us, right? So one of the main things I was tapped to come here and talk about is work with the Green 500, where reproducibility can be relatively interesting. Even verification can be tricky because of kind of unique issues with hardware, with actually doing measurements at these scales, right? So in the beginning, the closest thing we had to reproducibility was taking data sheets for hardware. And in some areas, that's about what you can do when it comes to reproducing energy efficiency data. Later on, as we get more information coming in, you can actually compare between multiple systems. That at least helps, but there are still problems. And so the question is, what do we do about the outliers? And some of the things that come up, I mentioned unique hardware. I happened to choose two examples from Japan, not really intentionally, but there are a couple of interesting things that came from there. Grape DR on the left, which looks a whole lot like somebody's Bitcoin mining rig, but is actually a whole lot of custom fabbed, custom processors created by one research group for one installation that never existed anywhere else. In fact, the winner of the current Green 500 list is a descendant of these parts, which is a little bit fascinating. But when it came down to verification, it was literally somebody getting on the phone with them and running multiple tests. But at the same time, they recorded a ton of information to try and help people reproduce this. But that hardware, it's nowhere else. And even if it were, they came down to changing the length of their power cables to try and get less power usage on this system. And then Tsubame KFC, the one on the right, or for those that don't know what Tsubame means, they were joking that the sparrow dipped in oil is fried like fried chicken, is another such system. They built an actual data center that was passively air-cooled by local wind conditions for this thing. Nobody can test this again, right? So we have to think of what we can do in reproducibility to deal with these things. And over time, we came up with the best we could, and that was to work on measurement methodologies. So at least if somebody could get the hardware, everything would be documented. This was a figure from the very first one that ever came out in 2007 from us, and it literally came down to make sure you have a nice CRT monitor, but hook everything up to 1 meter from one node and extrapolate. We do a lot better now, but over a course of time, we had issues even to somebody taking their measurement with a multimeter at a major US university and forgetting that they were running on a 220 voltage line and thus reporting a measurement that was twice as efficient as it should have been. There's the first deployed system for an architecture. Right. So as much as we work on reproducibility in computation and being able to run the software and get the same results afterward, doing work on computation that has to touch the hardware gets really interesting. And it's critical to have like well-established practices, things you can reference to actually get all the information to be able to reproduce these kinds of things, or to be able to reason about how correct a result is. And then I did not prepare specific slides for the rest of this, so I'm actually going to stop sharing here. But the summary is, even if we have great reproducibility initiatives, we have Jupyter notebooks, we have all these things, we still have to be able to actually build or actually run old software. And when it comes to Jupyter notebooks, who out here has used Jupyter notebooks recently? Right? I have. Who here has used a Jupyter notebook that's more than 5 years old and tried to make it work? A lot less people. We end up with a lot of interesting assumptions because the Jupyter notebooks don't actually necessarily document which version of Python they were built for, or whether they came from IPython or Jupyter or all the rest of it. And so as we go, there's other things that go into it that aren't part of actually running it, that aren't part of the data that went in, but they're part of building the environment that allowed those results to exist. Need to exist. They need to be preserved the same way. And I think it's still an open question how we do that. So is this a fad? No, I don't think it's a fad. But I think in a way we're still kind of in the infancy of doing this for computing, especially if we consider the whole platform rather than the part we actually run and the inputs we give it. So, thanks everybody.
Tom, are you still sharing? Are you still grabbing the screen? Good. Okay. Perfect. Right. Very good. All right. Okay. Excellent. Well, hello. Whew. Masks keep you warm as I go outside. I found myself with my mask on only to keep my jaw warm. We're adjusting to life. I'm Beth Plaley. I'm at Indiana University, where I'm a faculty member, and I direct the Pervasive Technology Institute as well. Delighted to be part of this panel. And I give credit to Lynn Pichard, who I worked with heavily on the survey that Tanu mentioned, that I'll be briefly showing a result on that is similar to what Tanu, on the same theme as Tanu's. The opinions, of course, are my own. So I've got a couple perspectives. So the perspective that what I have the benefit of is I came into the supercomputing reproducibility initiative last year in 20 after 5 years of hard work had been done to build up the ADAE process and to acclimatize the community to what they were doing. And that was a huge benefit. We chose to undertake a survey to get a sense for what the community was, the community perception after that period of time. So that's the perspective that I bring in. We published the survey. Lynn Tanu joined us and I just recently, and through that effort, I reflected on, these are my reflections on where I think some of the pain points and some of the opportunities are. Going back to what Dan Reed here was saying is it's about our rigor and transparency of the work that we're doing, the science that we're doing, and where some of those pain points are, which I agree with. I think some of those pain points are in a research environment that forces us to move fast and not necessarily as thoughtfully and carefully as we need to be moving forward. I want to point out, as I've heard it talked about in the panel so far, I just want to make the distinction between research results and projects, and we're reproducing the results, the research results as they are captured in a paper. We are not trying to reproduce entire projects, which may have multiple objectives and multiple research outcomes. And it becomes problematic when we try to reproduce the results of a particular paper because that data set can be used in multiple papers. Now we've got copies of data everywhere. And, so the problems are huge as people are identifying. But again, the reproducibility that we are talking about now is reproducibility associated with the results that are reported in our papers as they're published in SC. And also, I would argue that within a single paper, we're reproducing, a single paper can have multiple results. And when we say something is reproducible, does that mean the entire suite of supporting measurements need to be reproduced? I mean, if it's really the research result we're after, that should be the main focus. So a little bit of background on that community survey. It was done in 2020. We went back to the participants in the technical program over SC17, 18, and 19. That was almost 10,000 unique individuals drawn from that. The SC team helped us in reaching out to everybody. The response was quite low. I think this suggests that there's more opportunity to explore understanding the community sentiment again, but we did have 204 participants who responded to at least one question. Just because Tanu showed some of the results, I just want to highlight one result, and this is the one on scientific impact. If we're trying to reproduce, and what's the end metric there? Well, the end metric is that the impact of what we're doing is greater. So what we wanted to understand is are we as a community utilizing results? Are we utilizing that appendix information? And 35% of our respondents said that they had indeed used appendix information from other SC papers. I was very encouraged by that. Again, this is just, we need to dig into this to understand this better. But I thought that was a very encouraging response rate. And then did the appendices help me think differently about my own work or others' work? And the response was very favorable there. So we are having, the reproducibility effort is having an impact in both impact and in both the scientific impact and how one is thinking about their own work. So kudos to everybody who's been part of it. Coming back to the main point, I'm coming to my main point. Coming back to the point I made about rigor and transparency, and we need rigor and transparency in our process, and where are we interjecting to improve that? And as Lorena points out, rigor and transparency are both human values. Where I have a problem with what we're doing right now is, we're doing point of manuscript kind of checking, and that is as one is rushing to try to get a paper in. It's at that publisher that we're saying, no, we need to verify that this is reproducible. And if one takes that over the entire publishing industry, which I had the benefit when I was at NSF of thinking about, if one tries to just scale that out over the entire industry, over all the papers that come in, it is not a scalable venture. It is, and so to focus all your efforts in that point of manuscript submission is in my mind, it needs to expand beyond that. So, and this would be, when it's okay, when your reproducibility evaluation, and the point worth making here is the point of manuscript submission, reproducibility verification, when it has the potential to impact, accept, or reject decisions is when it becomes most problematic. Oops, I'm sorry. So it's problematic actually for 3 reasons. I added one later. So what are we trying to accomplish with our reproducibility at this point of submission, point of manuscript submission? One of them is we're trying to educate, and which I think is good. We need to train ourselves. However, that's like proposal submission time. That you don't use proposal submission moment to educate people because they're just not in the right frame of mind at that point. It's just a really bad time to try to make something a teaching moment. So we need to decouple education, the educational mission of the effort from that point of submission obligation. Those absolutely, they need to be decoupled. And as I mentioned, it burdens this point of manuscript submission, burdens the community in ways that simply aren't sustainable. And then also I would point out, if indeed the reproducibility evaluation is used in the acceptance or denying of manuscripts, then that process itself has to be subject to the same obligations of rigor and transparency as the original science is. And it's not some group of students that you're harvesting in who have not done this before that then decide whether or not your paper gets accepted. So I mean, that same level of rigor and transparency has to be applied there. And this is where the scalability breaks down. So I just thoughts to leave you with. So where can we move forward? My last slide here. We in computer science and computer and computational science have the unique benefit of putting a community in front of our journals, which is really what we're doing. We have these things called conferences. We publish in things called proceedings. We do peer review there. SC is a community that's basically a front to a journal, if one wants to look at it that way. That having that community gives us opportunities to do things that geo may not be the best example, publishing other disciplines that are heavily publishing journals, they don't have the opportunity of a community to mold the community. We do have that opportunity. So what could we do? We as a community could provide a venue, either at SC or associated with SC, where reproducibility studies count. Dang it all, they get published. They count in promotion and tenure. We could do that. Another thing we could do, and this is with decoupling our education, we have an amazing student program. We could shift some of that molding that needs to happen. Dan was saying we move too fast. We don't train our students well enough. We could call on ourselves in SC to provide some of those educational opportunities that would help nurture the community along and disassociate them from this point of manuscript submission pressure. So I know and I'm sorry, I'm too close to my screen here, so people are seeing half my head. It's like talking to my mom on the phone. You see just her nose and up. Anyway, or talking to my mom on Zoom. So anyway, so I wanted to, thank you, Dan, for letting me end on this note, and I hope this gives us opportunity for good discussion. I'm hoping I stimulated the discussion here. Thank you.
All right, now time for some discussion, and I'm watching the chat, and I also made some notes. So I'm going to throw a few provocative questions at the panel. So And in an attempt to be provocative, I'm going to say some things I may or may not completely agree with myself, but I want to try to charge some discussion. So I would make an argument that what we do is not science, it's mostly engineering. And what I mean by that is we're mostly reporting data on human-constructed artifacts as opposed to natural phenomena. And much like engineering in that sense, the thing that we're reporting data on may well be unique, but it is, there may only be one on the planet. Certainly at a high end, that's true. And Tom touched on some of those issues when he talked about energy measurement, reproducibility. So if that's the case, if you believe any part of that premise, this is a question really for the panel, how do we think about what elements of documentation of a perhaps unique system that may in fact not be replicable anyplace else? Do you really need to trust those results? So any thoughts on that from either our remote or our local speakers?
Right, so I would at least start off with that I think in many cases, especially when you're talking about energy measurements, especially at the very cutting edge or things that are custom designed, it's still important to be able to trust those results, one, to evaluate the effectiveness of the thing, but one of the main things we want to be able to do with those results, at least in the context of Green 500, other things like this, HPC, working group, et cetera, is make reliable results available so that it's easier to look across different kinds of hardware, different approaches to a problem to try and improve subsequent designs, right? So even if an individual measurement might be from a unique thing, you can start to draw conclusions about overall approaches from comparing several unique things that share similar designs, for example. And it really only works if we have a way to trust the individual components that go into it.
Other folks want to comment on that?
So, hello?
Yep,
Okay,
it's
all
on.
right, great, okay. So Tom, what would be what would be needed in the way of information to support this type of assessment?
Right, so a lot of the things that we actually try to get now is, rather than just asking for an energy measurement, we ask for the measurement, but we also ask for where it was measured, under what conditions. Was it alternating current or direct current? Were there conversion losses? Did you include the network? Did you not? It's the more information we have about how the measurement was actually taken, the more information we can derive from the result that we got. And that's where things like the measurement methodology help, is it gives you a shorthand for a way to specify a lot of that information without having to go into the details. Because one of the issues I tend to run into with this kind of reproducibility is that you get overload. If you want somebody to specify the exact meter and power supplies and everything in the setup, they kind of shut down. They just don't do it, or you get very few and then it's very hard to work with. So it's building up these conventions or ways to talk about these things without having to specify every individual detail, I think is really important. And that goes along with some of the reproducibility tools we've heard about, right? It's another instance of the same problem, I'd say.
All right, it looks like Tanu and Lorena both want to comment, so please go ahead.
I did want to make a clarification, and in particular to Tom, and refer you to the National Academy's report on reproducibility and replicability in science for the distinction between reproducibility and replicability. Because when you're talking about energy efficiency data, then this falls under the heading of replicability. And the National Academy's report draws the distinction very clearly on whether or not you're collecting any data. If you're collecting any data, it's an experimental setting, and then the definition of replicability applies. And in that sense, the definition says that what you're aiming for is to achieve consistency in the findings, and the results themselves don't need to match. The important is the scientific question and the conclusion that those results lead you to. So this is the definition in the national academies, and in this case, if the goal is to obtain new measurements, then under some definition of consistency of the findings, which is difficult, that is what applies. I think that it would be helpful to clarify that, to not focus on the wrong details for that application.
Okay, Tanner?
Yeah, I would echo what Lorena is saying, but maybe in different words. That yes, so I'll go back to Dan's comment that we are reporting. As scientists, we are reporting data. When it is data, well, metadata may just suffice with respect to complete reporting. But when we transform data, and that's where issues of reproducibility arise, have we obtained the consistent results or not? So when it's data and computation together, then the questions become much larger. And I would sort of go back to the phrase that Lorena used a little while ago of unimpeachable provenance. That we want this provenance to be associated from the very beginning. And some of the examples that Tom is giving, that's, well, how do I add additional metadata that when the data gets transformed, I have this provenance, this additional metadata to help me validate the result. I'll just stop there.
Well, again, some of this comes back to you may not be able to replicate it because it's a one-of-a-kind system only controlled by some people. So that speaks to another aspect of trust. I want to connect a different question to something that at the end that Beth said. So many people have argued that in computing we are held hostage by our conference culture, in that it has driven a focus on minimum publishable units that can be produced on an annual basis, and artificial deadlines as a consequence of conferences. And yes, it is true there are competitions in first claim of a result, but they're less common in much of what we do than there may be in other sciences. So in that spirit, the questions about deposit in journal-based disciplines that require data deposit, your paper will not appear until the data has been deposited. That's how the results are held hostage to ensure compliance. And that's possible because there's a regular cadence of publication that happens in many cases, in the case of Science or Nature, on a weekly basis. So in that spirit, any thoughts about how we might change the incentive culture about data and other infrastructure deposits in this artificially constrained world that we've created?
So I was encouraged, just a small success, but I was encouraged in the in SC20 in the reproducibility initiative, we swapped over to people giving us persistent IDs. and we saw persistent IDs being submitted. So I'm not sure that doesn't affect the community at all. But I thought it was encouraging that people were starting to think about the units of what they were producing. It doesn't change the timeline and the pressures of that, though.
Yeah, Fernando, your hand is up. And it looks like Tano's is still up too.
Tanu had her hand up before me. Go ahead, Tanu.
Okay, no, go ahead.
Yeah, so I would say that, with respect to changing the culture, it's, as our ADAE initiative has shown, that we have to be encouraging to authors. Sort of take this as a moment of education that we are producing experiments, and we are obviously producing them for conferences which are have a very strict timeline, that we give them a moment as to where their artifacts or their experiments are at this moment in time. It's not a statement of finality in some senses. It's not a statement that whether you're going to be accepted or rejected, but take this as a culture where we are encouraging them to improve this. Take this opportunity, from the point of submission to the end. There is 3 to 4 months. Take this as an opportunity to improve upon their artifacts and make it better. And there is, in some senses, a community and free feedback, I would say, which you get on your papers, get free feedback to actually improve the artifacts as they evolve over time.
And I'm sorry, go ahead, Fernando was going to say.
Fernando, please go ahead.
I just wanted to say that, and this is connecting the point that Dan brought up with a question about CI that was in the thread. And I think, in my experience, one of the things that has worked in some areas of this topic is just making it really easy to do the right thing, right? Most people are actually willing, absent kind of the outlier edges of fraud and kind of malfeasance, most people are willing to do the right thing. It's just that it's really hard. And Lorena has published some great work on how hard that is. And I'm not belittling those challenges, but there are ways in which we can at least lower the pain points and make at least part, if not capture everything, at least part of the more common needs and challenges, make them easier. And we have seen, for example, how in the open source community, the combination of tools like Binder, for those of you who are not familiar, Binder is a project that came out of kind of the Jupyter world that effectively, for any public Git repository that has its dependencies explicitly stated in a requirements file, in an environment file, it will automatically build and deploy a Docker container for you to share with a single click that has that repository pre-cloned, pre-compiled, and pre-built. And in many cases, basically, you don't have to do anything. If your repository is kind of sanely prepared, just having it there is enough to offer a binder link. And in fact, you can get a binder link for a repo that wasn't even prepared in advance for that. And if it wasn't done with anything too weird, it'll just work. That's some of what we teach our students. Basically, we show them, look, if you do this, and there's, by the way, a convention, if you have some special custom requirements, you make a binder folder and you drop a couple of files in there, and that's it. So the idea is if you do a few things in a certain way, and these are ultimately they're social conventions. I heard somebody say once that the big victory of Docker in the world was not a technical victory. It was just getting people to agree on certain things. It was a social win. And I know Docker doesn't solve every problem, but it solves some problems. And so this idea of preparing practices that enable the right thing, we see, for example, how aspects of Jupyter now have enabled binder links on every pull request. So literally, somebody proposes a pull request, which is a sub-branch of somebody's fork. There's an automatically created binder link for that, which means the reviewers don't even have to worry about figuring out what the person did. The pull request comes in, you click on their binder link, and you can see exactly what they did. It enables these conversations that Lorena was talking about to proceed on the right technical substrate, and that does actually change the culture. So there are more we can do in that direction. We'll not solve every problem, but I think we can actually make advances.
Beth, did you want to add something?
Yeah, no, I just wanted to add on to what Tanu and Dan, what you were saying, both Tanu and Dan were saying, is that we are creating our own problem by putting an artificial annual schedule in place, and then we're jamming stuff into it with the reproducibility, which is more work. So we're adding more work to an artificially induced schedule. So we are probably hurting ourselves with our own processes. And I agree with you. It's the conference deadline process that is hurting. That could be hurting us. It's an interesting observation. Yeah.
Hannah,
I just want to go back to Fernando's comment over here, and I've used Binder, and it's a great tool, but it has its limitations as well. Some of the research that I've been doing, Binder doesn't suffice for quite a few of the scientific use cases that we are doing. And I think as a community, it's up to us to also inform. There is no be all and end all in this world. There are things for which tools are the features that tools are supposed to provide, and they satisfy some form of it, but not all of it. Going back to Tom's comment, Jupyter notebooks, I mean, they provide literate programming in the best possible way, but they are not supposed to provide containerization or isolation. That's not what their feature is. So I think we have to, as researchers in the area of reproducibility and sharing and open source, put out the limitations of what something can do and what something cannot do as well.
Lorena?
Thank you. I wanted to add to Beth about the cycle of the conferences and some of the conversations, some of the chats and so on, a clarification on my point with bringing up open source software, the development process. And it is that to help to publish reproducible results, what we need to look at is how we do things from the beginning and from the inception of a project, including how we train the students, how we what tools we use for collaboration, what the ways that we coordinate as teams in distributed fashions, especially now, of course, remotely. And with the goal of managing complexity so that the highly elaborate projects in the context, of course, of high performance computing become more transparent because of these processes and ways of working, because like Beth said, at the point of manuscript submission, it's too late to make a project transparent. The best that we can do is to deposit some artifacts, but that is also usually not even possible unless you've managed the data from the beginning in a certain way. So when we talk about data management, it's something you do from the beginning. It is not something you do at the end, at the publication stage. The same with software, with results, with the record keeping. And what I propose is that open source development is simply a template for a successful way to handle complexity and improve quality in highly complex technical scenarios.
So I want to take us in a slightly different direction. We've been talking about reproducibility largely in the context of science, and the implicit assumption is that there are two failure modes, either induced errors or fraud, fundamentally. But HPC is only in part about science. It's used for lots of real-world applications, as I was trying to touch on Monday night in the plenary panel. So there are lots of issues around non-reproducibility and even non-determinism in those deployed applications, which relates really to trust and what I would describe as critical infrastructure. So it's a related issue. Let me give you a concrete example. If you think about a near real-time weather forecast, there are literally people's lives and property at risk based on errors in those models. So it's not just a case of scientific accuracy. And we know that if you look at the US versus the European models, they are actually quite divergent in many cases in their underlying assumptions. So how do we think about building that broader trust beyond science in computation? What evidence do we need to provide to assure people that we've done our own diligence and rigor in supporting the underlying hardware and software? Thoughts on that?
If you don't mind, I guess I'll start us off for a second. This is something I didn't really bring up in my introduction, but it's something that we end up running into quite a lot working with the DOE and the NNSA. Some of the results, you're talking about weather that may really impact people's safety. It may be national security. It may be any number of absolutely critical things. And verifying results is really important, but also the reproducibility, and when it comes to some of these highly critical results, I mean, there are literally mandates for 5 to 10 year reproducibility, save every last scrap of every bit of data so that we can look at all the past results to try to verify new ones, but also so that, well, frankly, if something goes wrong, we can find out what and why. And I think there's a kind of a big scale here when it comes to how critical that is, when it comes to whether you might want to look back to try and refine models for the future, but how long do you store every intermediate output? Is it something that's as critical if you know what the weather actually was on that day? And that I think it's really an open problem how we get to a point where we have sufficient trust in these things. But the importance of the result, I think, helps inform what the reproducibility or the replicability needs to be in these cases.
Beth?
Yeah, okay. Yeah, thank you. These are really wonderful questions. I think we ought to provide a venue where we can publish why a particular weather forecast system or whatever should be trusted. We should write that in lay language, and it should count as a broader impact, a significant broader impact of our proposals. So it puts the obligation on us to make the step towards the society that's trying to trust us. And we take that step, and I think we need to increasingly take that step.
Yeah, I'll just remind people of an old quote from the late Richard Deming, who said, "The purpose of computing is insight, not numbers." And that, after all, is the reason we do these things, is to gain insight into phenomena. Well, I'm mindful of the time. We have about 7 or 8 minutes left, and I'd like to ask each of our panelists if they have any parting comments they would like to share. So I will start with Fernando.
I am mostly curious as to what we, when I think of the community that spans Jupyter and deployments of Jupyter in larger scale projects like Pangeo, the 2I2C collaborative that we now have kind of launched last year to have more deployments of Jupyter in research and education. What input does the community have for us? And I am close to some of the folks in HPC. I work closely with my LBL hat with the team at NERSC and also with folks at NCAR in HPC facilities. But what are things that we could do that would make that aspect of interactive computing that Jupyter facilitates? And I recognize Jupyter is not the only tool in this space, but we are a widely used tool. What can we do to make the workflow, the daily workflow of those of you who are deep in the HPC world, which I only touch upon in my own practice occasionally, but not regularly, what can we do to make your life easier and better in this regard? We are open to input. We continue to develop and build a project, and ways in which we could make those processes easier will be welcome, and we will listen, and I'm happy to connect with anyone who is interested in that, in kind of work that we can do for that. And we can test ideas in that regard, at least at NERSC and NCAR and other places where we work closely with the teams who run the machines.
All right, terrific. Lorena?
Thank you. Maybe what I want to add is that in the process of building knowledge using computations, which we use at all scales, from running a statistical analysis on some small experiment to, of course, large-scale simulations of climate models and so on. And hardly any scientist today doesn't use some form of computation. At all levels, there is a portfolio of different trust-building activities that we have and need to pay attention to. On the one hand, we talk about reproducibility and replicability, but of course we also have in simulation settings validation and verification efforts. We also have in other settings in AI, this is a open question about explainability and interpretability of models. And some people are talking about algorithmic accountability and being able to go back if something is detected in terms of bias of an algorithm, to be able to go back and inspect it in some way similar to like the National Transportation Security Board inspects accidents and so on, to have a way to do constant monitoring and then also investigation of specific events that are worthy of it. So we have like a multi-axis space of trust building and credibility building activities that we need to attend to. And I think it is in our purview to look at them all and see how they all interplay. And the one I didn't mention, of course, uncertainty quantification, requiring elaborate statistical approaches. And these, we should keep them all, look at them all in concert, is what I wanted to add. Thank you.
All right, thanks. Tanu?
Yes, so I'll say my parting comments wearing two hats. First, the hat of a researcher that, this whole idea about reproducibility, we've sort of discussed that, depends inherently about on provenance. And auditing provenance, is expensive. And HPC is all about performance. So we have this trade-off over here, which opens up a wide range of possibilities as to where provenance itself should be audited. And same goes with containers, which is something that I've been working on, that provenance auditing and containers, which is isolation, are contradictory to each other. And so how can we bring these fundamental concepts which will enable reproducibility, at least from a tool perspective, in a broader sense? So that's one from the researcher side. And from the organization and policy side, being an ADA co-chair, I would say that, in my experience, the enthusiasm of the authors was very high. I think it's for us upon as a community that how do we sustain this effort through organization, and particularly for SC, because there is a huge investment in resources. A huge number of experiments are done on large-scale facilities. We need something which is not at the point of submission, is much earlier, where experiments and authors can come and do use these resources much earlier in a reproducible way, so that things can be done once their paper, or things can be verified once their paper is accepted. All right. I'll just stop here. Thanks.
Tom?
Sure. So actually following a little bit on what Tanu was saying, I mean, and Dan and Beth made great points that we have problems getting things verified when it's at the paper submission time, right? And it's a problem with throughput, it's a problem with availability, it's a problem with all kinds of things. But we've talked about really, if you think about it, there are two ways that you try and get change. You try and force it, or you try and encourage it by giving some benefit, right? And a lot of the initiatives we've had, at conferences, they're saying you must do this to get a paper accepted or to get some benefit. There's, what Fernando was saying, making it as easy as possible, making it the natural thing to do gives people some benefit. And finding more ways to encourage this, to make it part of the culture, the easiest thing to do, but also to have some way that authors or institutions or others accrue benefit from doing it, or from doing it properly, can really help. That ended up being something that helped us on the Green 500 much more than we expected, actually, was just giving people badges based on how essentially useful or high quality the data we got was. Made a substantial difference in how much people were willing to put into doing it, because it gave them something they could brag about, and that's literally all it was.
All right, Beth, you get the last word.
I do, yeah. So call out to Natalie Bates, who approached me a year ago to talk about the issue of energy and reproducibility in energy. Natalie, thank you so much for raising this topic. I think it's been a wonderful discussion. I'm in total alignment with the others, Tanu particularly, in continuing the conversation about how we improve our thinking about reproducibility for the high-performance computing space. And thank you all for being here and being interested. And Dan, thank you for moderating.
All right, folks, that's a wrap. Have a great year. I really, really hope we see you in person next year.
Yes,
All right.
absolutely.